Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer. I'm Desire, and today we have Nicola, who has completed the course Linux Basics, and he'll be giving us a presentation to explaining how he has managed to go about the project. So first of all, like we always do, we'll see a demonstration on the real robot, and then we'll get into the nitty-gritties after we have seen the demo, and as always we'll get to ask him a couple of questions towards the end. I will now hand over the platform to him so he can begin his presentation. Okay, Nicola, whenever you're ready.
All right, okay, thank you. So I'm actually connecting to the real robot environment. Wait a few seconds.
All right.
All right, okay, so I can place this right here. So first thing first, I will open let's close this. Let's see if it closes. Let's move a bit. Okay, so I'm opening the terminal, and first thing first, we need to get the robot going. So we will write a couple of lines in this terminal. So now I need the symbol. And then slash simulation workspace slash install slash dot bash.
All right.
Second, we can launch our program. So ROS2 launch with the Turtlebot. Main dot launch XML. Okay, so in the meantime, while a RVs is opening, let's see. Okay, so I can move this down here. Let's zoom it a bit. Let's reduce so everyone can see. Now, in a second terminal, what we need to do is we need to launch the robot interface program. So what we write is cd change directory, and we search into the directory that we need. So in the ROS2 workspace, source Linux basics project slash Linux basics project. So I probably yeah, I wrote something. Control C, Control V. Project. Okay, if we type ls, we will see basically the files that we need. So we need to launch the robot interface.py, which is actually a Python program.
Okay.
.py, which contains basically, it allows us to connect the robot node which works with its own sensors and control systems and allows to do many other functions. Once it prints the message ready, then in a third terminal, we can actually launch our obstacle avoider program.
Okay.
So similarly to what we have done here, we can actually pass this line here, the correct one. Okay, let's pass this and correct it. Control C. Project.
Should be fine, I think. Yeah, there we go.
Yes, ls, and so we'll see the obstacle avoider.bash. So /obstacle avoider dot bash.
Okay.
And let's wait for the program to run. Now I will explain it briefly what it's actually doing, and then we will go into details in the code lines. So actually, it's getting the front, left, left and right ranges values. We will see if they are below or above a certain threshold, and based on that values, it will output some action for the robot to do.
Okay.
Those outputs are the logic behind is binary logic, so it's 1, 0. So if, for example, the outputs the 1 means that a certain direction is free, so the robot will move accordingly to that direction. If it's 0, it will do another action, for example, turning, as it's doing right now, or moving forward for a certain distance, and then stop. So the robot actually is doing is turning. In the meantime, while this code is working, we can actually make work also the robot statistics program, which is a program that displays the robot statistics such as the odometry. So we will see what we mean. So Control C. We'll go into the right directory, and we have the robot statistics. So similarly, robot statistics dot bash robot statistics. Is it right? Statistics. Yes. Okay. And basically it gives some odometry information, such as the distance covered up until now, the direction, in this case southwest, the odom position in the X, Y, and Z, since of course the robot is moving in a plane, so in a 2D space, let's say like this, so the Z coordinate is set to 0. Then we have some values of the orientation of the angles, the roll, pitch, and yaw angles, and the angular velocity and linear acceleration. And in the meantime, the naive obstacle avoider is doing its work, so is setting the ranges, is checking if they are below or above a certain threshold, and according to that, now the robot is actually rotating. Okay. So if we want to look into details of what those code actually do, let's open the code editor, and let's go into the obstacle avoider file. So first thing first, we included the shebang line, which basically tells Linux that what we are writing right now is a bash program, which works for Linux, much like a Python program works for Python or a C and so on. Then the command source, basically we include functions library. It's a robot function library that I wrote previously, which contains a set of getter and setter functions, which, as the name suggests, gets some values. So, for example, the right ray range, front right ray range, or the angular velocity, the command for the linear velocity, and also some odom position, odom distance, odom orientation that we are able to see actually in the robot statistics code. Then, going back, so we print some messages, and we set initially the linear and angular velocity to 0. We set a threshold to 0.3, and we first scan all the 5 ranges that we need. So the front left, front right, left, and right.
Okay.
Then we check if those front scan ranges are less or higher than the threshold. If higher, like in this case, we print with echo front free. So we print that, we say that variable front free or front left and so on is free actually. And then we can start with our logic. So first with an if condition. In this case, they are all set to 0, the three front ranges. So we are asking the robot to check the direction which to turn. How?
Okay.
You will check if the left range is greater than the right range. If so, you will turn, of course, to left with a certain angular velocity, otherwise to right. For example, if we check the second in the elif condition, so is an alternative. For example, the front right range is free. So, of course, front right, the robot will turn right if the other two are 0, for example, with a certain angular velocity.
Okay.
And then after certain amount of time, set to 0. Same thing, for example, with the front free. Now, front free is free, actually. So we set the distance to move, which is the front range minus the threshold, the value of the threshold. A time to move, we print those values. We assign to the robot a certain linear velocity. And then after the robot has moved to a certain point, it will stop. And so on with other elif conditions, so different combinations. So the robot, again, based on the values of the ranges of the scan of the LiDAR, it will know if they are the values below or above a threshold, and based on that, it will compute an action.
Okay.
And so on with all this. In the robot statistics, instead, what we do is we print some ODOM functions that we have also previously seen in the getter setter function. So the ODOM direction, the position, the IMU angular velocity, the linear acceleration, and basically we see them in the here, plotted here. They are printed inside the this one, the terminal. All right. What else?
Are you still going to use the slides? Did you say you had any slides?
Yeah, I did a presentation. If you'd like, I can quickly just present it.
Yeah, it's fine. Let's go for it because you've got about 8 more minutes left now.
Okay. All right. So it's a really quick presentation. So let's close this window. Let's open this one. All right. So basically, just a recap of what I have done so far with the project. So basically, the objectives were, as I said, to write and implement a naive obstacle avoider program and a robot statistics program and test them first in the gazebo simulation and in the real robot lab. Okay. So first, I got to know the robot, which, as we know, has a LiDAR 360 for navigation, then the environment. As I said, it's all involved around the turtlebot orientation. So with the three main codes: robot function, naive obstacle avoider, and robot statistics. Okay. First thing I did was a test. So I tested the naive obstacle avoider. I checked the results, and actually gave me some problems because the robot was turning around itself. Okay. I understood those problems where basically I missed the reset of the angular velocity, some elif mistakes, basically some conditions were the same in two different lines, but with different results. So the robot was basically confused. They were in contrast with each other, and some indentation error. Then, as I showed you earlier, I corrected with the right code that I showed, robot statistics code 2, and the robot worked both in the simulation and, as I showed before, also in the real robot lab.
Okay.
So this is a recap of what I have done so far.
All right. That went pretty quickly. It was a very nice presentation, though. I like the illustration and the graphics.
Thank you.
Very, very well done. Do you have any other bits that you would like to show us? Because you still have a little bit of time. Otherwise, I can get into the questions.
No, you can get to the questions.
All right. So, if you remember the very first time you ran the robot, right? I think it collided with one of the one of the
obstacles.
Objects. Yes.
Yeah.
What are your thoughts about that? What do you think could have not happened the way it should in the script, or just general reasoning? You don't have to get into the details about Linux or anything. Just from the way you program.
Yeah. Yeah, probably maybe some error occurred in the beginning. Maybe it detected the range wrong, so maybe it was a slight above the threshold, so it didn't detect it quite accurately. So he considered there was no object in the middle, but actually it was.
Yeah,
So
true.
sometimes maybe also because there were two let's say two objects near each other. So maybe he detected the one further, but not the one closer.
Yeah.
So as he moved, then he encountered so it might be an explanation.
Yeah, yeah. I think
Um,
I like it. I think you have reasoned very well there, because normally when the object is smaller, sometimes it takes time to detect, right? For example, the ones that it bumped into, they have a very narrow stand, right? So sometimes
yeah,
it might be moving and it doesn't pick it up on the first scan. So yeah, that was quite good, because you do notice that it stops when it gets to the wall or any object that's bigger.
yeah,
For example, the one that's
yeah,
next to um, that's slightly bigger than the round ones, the rectangular one right in front of it right now. So yeah,
yes,
very good reasoning there. And the other thing I wanted to ask you is, you spoke about giving permissions to a file to execute, right?
yeah,
Can you explain to me
yeah.
how that happens? What command do you use?
Yeah, so basically, permissions are used. It's a way to guarantee some security to Linux
Mm-hmm.
because usually when we create a directory and we create a file,
Mm-hmm.
we need to set those permissions with, for example, first of all, we can differentiate a three permission commands: read, write, and execute.
Mm-hmm.
Read, as the name suggests, we can only read that program. Write, we can also write inside. But if, for example, we don't have the execution permission, we actually cannot execute the program.
Mm-hmm.
And we also have some groups that have or not some permissions: the owner, the group, and all user.
Mm-hmm.
So usually when we create a file and we execute it, it may give an error. And so a way to check if there are the permission is with the command chmod.
Mm-hmm.
So with the command so first thing first, maybe we can also, for example, when we go into the directory,
Mm-hmm.
we can check, for example, let's say, whether a particular program has a permission or not with the command, sorry, command lsla. So let's try it. So I'm making. So as I said, with the command lsla, we are able actually to see what kind of files are inside project lsla.
Mm-hmm.
And we see on the left some RWRR. Those are the permissions. So R stands for read, write, and then X execute. So
Okay.
with the command chmod, we can actually modify those permissions. For
Mm-hmm.
example, in the second one that I'm indicating, the owner, which is the first one, has read, write, and execute. So it has all the permissions.
Yes. Yes.
Instead, we can maybe subtract some permissions to the users or to the group. In this
Yes.
case, users do not have some permissions, and so the groups.
Okay.
So it's a way to control which people can access or not to some files.
All right. All right. Very well done. I love the detail. Very nicely. Um,
Thank you.
the other thing I wanted to ask is concerning the the use of the grep command, right? So can
Yeah.
you explain to me a little bit how it works, and what exactly does it do to your console output, for example?
Well, for example, if we open a certain directory, we may have a lot of a list of files, and maybe we want to access or we want to get a specific file, and grep allows us to basically intercept that file by
Mm-hmm.
writing in the command grep and the name or a word associated with a specific command or a specific, file that we want to get.
Mm-hmm.
So it's a faster way to get to the file that we need.
Mm-hmm. Okay, I see. So can you say it does some form of filtering to your output, right? Let's say
Yeah,
if you use
actually,
it with
it
LS.
is a filtering. Yeah.
Okay, all right, that's good. Okay. The other thing I wanted to ask is you did some processing of scan data, right? Can you take me
Yeah.
through that process? How did you use bash commands to process that data or filter the data to put the scan ranges into the 5 compartments that you have got, right? Front, right, front, left. You can
Yeah.
use the script as well to
Okay.
just explain. Yeah.
Okay, so in the beginning here, I basically scan all the values. What I did, I have associated to the values, to the ranges that I wanted, in the name of a certain variable.
Mm-hmm.
With this dollar sign, I refer to the specific value that I want, get scan front three ranges, get scan front left, which are basically took from the robot function bash file.
Mm-hmm.
So if we go inside the robot function bash, we will find them. And basically, they communicate with the robot interface.py program,
Mm-hmm.
where it's a bit more specific program that I didn't modify, of course. But
Mm-hmm.
inside that program, as we may see, so we have extracted, we have get the parameter, the value of the front range. And inside that program, basically, he communicated with the robot, so the lidar was working.
Mm-hmm.
And thanks to that file, to that code, we were able to extract the specific scan range that we needed.
Mm-hmm.
So once he detected that value, we put it inside the getter function, and we recalled it inside our obstacle avoider file.
Mm-hmm.
And we did for all the other ranges. And then with the echo, we just printed the value with the meter, so indicating the value in meters.
All right. I see. All right, Nicola. It's a very nice presentation and very well done. I'd like to
Thank you.
congratulate you on the clarity of explanations and also clearly demonstrating what you did, why you did it, and on top of that, just the general thought of trying to figure out why did it bump into the obstacles at first, and that's quite nice because you do have to think about these things as things do happen, right? Because you will get to a point where your robot does things you don't understand. You have to think about them to find out what could it be that went wrong with your code or that did not happen the way you expected it to happen in your processing loop. So I really did like the way you thought about it. So what we'll do is we'll wrap up here, and then I say just hang on. We'll finish our conversation on Zoom. All right.
All right. I can close the
Yes.
Okay.
Yes, you can.
Okay.
All right, everyone. So this was Nicola's presentation. I would like to congratulate him on a job well done, and would like to say to all those who would want to give a try to the courses we offer certification on, we highly encourage you to do so, and then you can come and present, as this will enhance your learning. We believe that teaching is the best form of learning as well. So until next time, keep pushing your ROS learning.